In this video, we are going to continue naming hydrocarbons. Now we are going to focus on alkenes and alkynes. Alkenes and alkynes are hydrocarbons that have the chemical formula CnH2n for alkenes and CnH2n minus 2 for alkynes. Alkenes, as we learned in the previous video, towards the beginning of this video series, they have a double bond, at least one. On the other hand, alkynes have triple bonds, at least one. So when it comes to them, because the carbon atom has these double bonds or triple bonds, understand that these molecules are known as unsaturated hydrocarbons. And in essence, it is because they do not contain the maximum number of hydrogen atoms than carbon can hold. An example of an alkene, as you can observe here, is lycopene. Lycopene is the molecule that it is responsible for the redness that we see in tomatoes. It is actually an antioxidant. And as you can see from the ending of the name, lycopene, we can see that that "ene" ending indicates that we have alkenes in the structure. And when you look at the structure, you can see that there's many alkenes in lycopene. Let's now proceed to learn how to name alkenes. When it comes to naming alkenes, you're going to find the longest carbon atoms, but in alkenes, it must contain the carbon-carbon double bond. Then, in this longest parent chain, instead of ending with "ane", you're going to end with "ene", indicating that you have an alkene. We're going to number the carbon atoms in this parent chain from the end that is nearest to double bond. So the double bond gets the priority. Now, at times, we have to understand that there are some alkenes that are actually equidistant, meaning that from either end, they're going to have the same numbering. Only then, if you have an equidistant double bond, then you're going to select the numbering starting from the first substituent. So that is a special case. Then, as you can see, you're going to indicate the position of the double bond by giving the number of the first carbon in the alkene, and you're going to place that before the parent chain, and then as a prefix of that, you're going to place the substituents. Please do not forget the rules that we learned for one substituent, multiple of the same substituent, or different substituents. Let's actually do these two problems for alkenes. Here we have the following alkene. When we find the parent chain, we can observe that we have 1, 2, 3, 4, 5 carbons. I went left to right because that is the end that is closest to the carbon-carbon double bond. So this is carbon 1, this is carbon 2, 3, 4, 5. So before, we learned that if we had an alkane, we will write the word pentane. But because this is an alkene, pent gives me the number of carbons in my parent chain. Ene tells me that I have at least one carbon-carbon double bond in the molecule. As you can see, the carbon-carbon double bond is between atoms 2 and 3. So I'm just going to put the value of 2 before pentene to illustrate that that is the first carbon in the carbon-carbon double bond. In this molecule, I have two substituents. They happen to be the same. They're both methyl groups. And as we learned previously, when you have two substituents that are the same, you're going to write the name of the substituent. You're going to put the prefix di to symbolize that you have multiple of the same. And then we're going to give their position. One is on carbon 2, the other one is on carbon 4. Let's move on to the other example. Here we have another alkene. In this alkene, if I number it left to right, 1, 2, 3, 4, 5, 6. Let's observe that if I number this 1, 2, 3, 4, 5, 6, this is considered an equidistant alkene because the numbering from left to right and from right to left places the alkene between carbons 3 and 4. In order to break this tie, we're going to select the numbering that is closest to the first substituent. So this is that special case that I talked about in rule number 2. So because of this, the correct numbering is going to be the red one, not the blue one. In this molecule, I have two substituents, one on carbon 1, one on carbon 5. Since I have 6 carbons, my parent chain name is going to be hex for the 6 carbons, ene because I have an alkene. The first atom in my carbon-carbon double bond for the alkene is a number 3. In these substituents, I have to put them in alphabetical order. On position 1, I have a fluoro group. On position 5, I have a methyl group. And this is the name of this alkene. Here we have names of alkenes, and we can actually draw their condensed and skeletal structure. So I'm going to practice with the first one, 3-ethyl 1-pentene. In previous videos, we actually learned that whenever we are given a name and we need to draw something, we need to start from the parent chain. Here it says pentene. So pent refers to 5 carbon atoms. 1, 2, 3, 4, 5. This position 1 tells me that my double bond is between carbons 1 and 2. Then I have one substituent on 3 that is called an ethyl group. And an ethyl group looks like a CH2 bonded to a CH3. And when I have a condensed structure, I need to write the correct number of hydrogen atoms for each one of the carbons that I have here. So when I place the hydrogens, it will go as follows. The first carbon is going to get 2 hydrogens. Carbon number 2 gets 1. Carbon number 3 gets 1. Carbon number 4 gets 2. Carbon number 5 gets 3 hydrogens. Remember that the placement of the hydrogens is to complete the octet of the carbon atoms. And since these are hydrocarbons, then hydrogen is what fulfilled the octets of this molecule. Let's now draw the skeletal structure for this molecule. So for 3-ethyl 1-pentene, I need to write carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5. The carbon-carbon double bond is in between 1 and 2. And then on carbon 3, I have an ethyl group. So that will be the skeletal structure for this alkene. Make sure that you practice with the rest of the alkenes that we have present in the following slide. Let's now proceed to learn how to name alkynes. The rules for alkynes are actually very similar to the ones of alkene. We're going to find the longest carbon-carbon chain, but now this longest carbon chain needs to have the triple bond within those atoms. Because it's an alkyne, then my parent chain is going to end in -ine. We're going to number the carbon atoms starting from the end that is closest to the triple bond in this case. Sometimes we can have alkynes that are equidistant, just like we saw for our alkenes. And understand that we're going to indicate the position of the triple bond by giving the number of the first carbon in the alkyne. And we're going to place that before the parent chain. And then if we have substituents, let's remember that we have to place them as a prefix of the parent chain. Let's do the following examples. Here we have an alkyne. In this molecule, we have 1, 2, 3, 4, 5, 6, 7 carbons. I have to number this starting from the end that is closest to the carbon-carbon triple bond. So my parent chain, since it has 7 carbons, that means that specifically half is my prefix for the 7 carbons. Because I have 1 carbon-carbon triple bond, this is heptine. The first carbon atom that is holding that triple bond is carbon 3. And then I have only one substituent on carbon 6, which happens to be a methyl group. You can see it right here. So this is 6-methyl, 3-heptine. Let's do the other example that we have here. For those students that are not familiar or skeletal structures may be a little bit intimidating, understand that the skeletal structure can always be changed into a condensed structure. Let me illustrate how you can do that. So, in an alkyne, this is the first carbon atom that has 1 hydrogen. This is another carbon atom, but because it's sharing 3 bonding pairs with the CH group and 1 bonding pair with this carbon, it doesn't get any hydrogens. The carbon atom that has that CH2, CH3 has a hydrogen. This is a CH2, this is a CH, this is a CH2, this is a CH3, this is a CH3. So the first thing that we have to identify is what is the longest carbon chain of atoms here. When we explore throughout the molecule, we see that the longest parent chain is 1, 2, 3, 4, 5, 6, 7 carbons in length. In this molecule, we have 2 substituents. Since we have 7 carbons in our parent chain, we put the prefix hept. Since this is an alkyne, this is heptine. The first carbon in our carbon-carbon triple bond is position 1. And then since these substituents are different from one another, we have to put them in alphabetical order. Let's not forget the rules for when we have different substituents in an alkyne, or in general for when you have it in a hydrocarbon. So on carbon 3, I have methyl. On carbon 5, I have a methyl. And then the parent chain is 1 heptine. Let's practice now going from name to drawing the structure for an alkyne. I'm going to utilize the first one, 4-methyl 1-pentyne. If my alkyne is pentyne, that means that there's 5 carbons in a row in my parent chain. The 1 before the pentyne illustrates that there is a triple bond between carbon 1 and 2. At position 4, we have a methyl group. So if I number the carbon atoms, 1, 2, 3, 4, 5, on carbon 4, I have a methyl group. Then I complete the octets of the remaining carbon atoms. Carbon number 1 gets only 1 hydrogen. Carbon number 2, no hydrogens. Carbon number 3, 2 hydrogens. Carbon number 4, 1 hydrogen. Carbon number 5, 3 hydrogens. Remember that carbon needs 8 electrons. And since an alkyne is a hydrocarbon, we need to fill in the octet of carbon with hydrogens. When we do the skeletal structure, let's understand that specifically an alkyne is a linear molecule. So that carbon-carbon triple bond is a linear molecule. So if we do 1, 2, 3, that's going to represent carbon 1 and 2. So from carbon 2, we're going to do a line. That's going to be carbon 3. And then after that, carbon 3 is actually tetrahedral. So we're going to go 1, 2 more carbons to represent 4 and 5. And since the vertex for carbon 4 is pointing down, then that methyl group is going to be pointing down. And that's the skeletal structure for 4-methyl 1-pentyne. Make sure that you practice with the other problems that we have in the slide.